so now we're going to do some activities that are going to model pretty closely a few of the activities that we're going to see in 520 and 410. We like to get the students obviously up and moving around, and some activities are a lot more conducive to that than others. And so I'm going to start demonstrating just one idea on solving equations, and the fact that we have a couple of activities in Math 520 which are fantastic, which really get them to see on the computer the idea of balancing equations as a balancing of scales, and the fact that if you do some task to one side of the scale, then you have to do that same task to the other side of the scale. Another way to describe that is through using number lines to demonstrate solving equations. So I'm going to give a few of you maybe that didn't have an opportunity to get up and do the cotton ball activity, a few cards to start with here. So let's just say that this here is our equation. Okay, the equation is 5x plus 3 divided by 2 equals 9. I'm going to put this up and then give a few of you some opportunities to do this. So the idea here is that every change that happens in an equation and an expression has a corresponding change to the number line. So if I wanted to locate the fact that 5x plus 3 divided by 2 is equal to 9, okay, then I would put 9 in an appropriate spot where it's supposed to be. So obviously if 0 and 20 are in this location, then 9 there's halfway. So I'd probably shift 9 somewhere about to there, perhaps, okay? Which means that 5x plus 3 is the exact same location on the corresponding number line, okay? So every change that you do to an equation, every time you do some operation to an equation, you have a corresponding change to the number on the other side. And obviously when we start to show them this idea, you know, it's a little tougher to make that transition when you have variables on both sides, for instance. But that's not really the point. Obviously, when we're showing them, as I'm going to show you in a few minutes, some cool ways to teach, especially for 520, dividing fractions, multiplying fractions, you show them how they should be visualizing and what they could be thinking. But then eventually they have to make that abstract jump to be able to do some more challenging problems, right? So I'm going to have. Let's see, how about this one? So this would be the next step. So obviously, what would the next step be if I wanted to solve the equation 5x plus 3 divided by 2 equals 9? Multiply both sides by 2. So Hira, why don't you go up there and put where you think the expression would be that results in the next step?
So I have 18. This is really close over here. To multiple 2.
Right. So if I multiply 9 by 2, then 18 gets closer to 20, which means that if I multiply the expression that was equivalent to 9 by 2, then that expression should be the same place as 18. Okay. So now we've got another one here. Let's see, we have this one. How about me? Okay, so what would the next operation be here if I wanted to continue to try to get the value for x? Subtract 3, sure. But if I subtract 3 to both sides, we get 15 for the number. And so this is giving us a visual. They can see on a number line where numbers are, where the integers are. So that operation had a corresponding change as well. There you go. Yeah. So we should be able to see at this point, if 0's here and 9's here, 18 is twice as far and 20's at the end. That's about right. Right? But we're still not quite to the place where the value of x is represented. Right? So Glenn, why don't you go do this last one. So obviously if I wanted to get x by itself there, and I know that 5 times the value of x is 15, then what would the value of x have to be? Sure. And this gives us a good, thank you. And this gives us a good way to discuss whether or not the spacing is correct. And we have another great activity that I won't go over today, but another great activity in terms of hanging it's called a clothesline number line, where you can hang 0 and 1 and have them come up and locate where the fractions are, what the fractions represent, and what does 1 over 3 mean? What does the 1 represent? What does the 3 represent? And so they're actually placing them on the number line so they can see how those are located. right? And so does everybody agree with the placement? Everybody agree with the location? Pretty good, I think. There is another activity. If you open up some papers that have a lot of squares on them, okay, it's all stapled together, and there's going to be some other activity pages that happen right after that. So you could go ahead and open that up. So oftentimes when we're describing fractions, a lot of times we discuss them in terms of circles. And if you're eating a pizza and somebody eats half of the pizza, then what does the other half look like, right? So we think of them as circles, but there's a real advantage for operations of fractions if we think about the whole as a square, that we're going to see in a couple of minutes here. First thing I'd like you to do is just take a few of those squares and determine a way to partition that whole. We're going to think of squares as the holes right now, into 2, 3, 4, 5, 6, 8, and 10 equal vertical parts. What do we mean by vertical? Yeah, straight up and down, like columns, straight up and down, right? So why don't we just start off by doing 3 and 4? Okay, just to get an idea of that.
3 equal?
3 equal vertical parts, that's right. And then in another one, do 4 equal vertical parts. So obviously, if we break these up into each part, then the next thing here I would ask the students to do is to write each whole as a fraction. Because if I know that I've broken this whole, this is one whole, then I know that all of these are still one whole. It's just that I've shaped them. I've just cut them into equal parts. And so if this is 2 over 2, then that means that I've got 2 pieces out of a total of 2 pieces. So why don't you go ahead and write each of your fractions as a whole, right? The fraction as a whole, or rather a whole as a fraction. So of course we all know that that would be the same numerator and denominator, and this is a good time to start talking about what the numerator and denominator are. So what would you say that the top number, this numerator, actually describes? How many parts of the whole? Okay. How is that different than what the denominator describes? So it's the number of parts of the whole. Okay, so what's the difference then? So what does that bottom number tell us? What does that top number tell us? So I think it's best to start with that denominator, that bottom number. What does that bottom number describe? The number of total parts of the whole. I think that's important to actually recognize that it's the total parts that I've broken the whole into. That 8 represents the fact that I've cut it into 8 total parts. So what about the numerator? How many are shaded? I don't see any shaded here, but you're right, absolutely. It's the number that you're choosing, perhaps. The number shaded, and that's how we typically represent it, right? Very good. Okay, but these all have names as well. And I feel that we're very big in MATHSway on terminology and vocabulary, which I don't know, I didn't always focus as much on, but when we start talking about polynomials, for instance, and Elizabeth's going to talk to you about that in a little bit, we bounce these numbers around, we bounce these terms around, right? Denominator, binomial, monomial, fifths, and so on. But sometimes we say it without really thinking whether or not they know it. So the next thing we want to do is write each fraction in words. So physically write out what you wrote here. So 4/4 is how we end up writing that one. Go ahead and do the other ones, you did. When you broke yours up into 3 parts, what did you name that whole? 3/3. So if you look at this, there's an interesting idea between the first word and the second word. Right, so what exactly do you notice about the first word? It's a number. 1, 2, 3, 4, 5, 6, 8, 10. Those are counting words, right? The words that we use for counting. And so essentially, what does the second word describe? What? Units, parts. It's a noun, right? It's actually naming that size. I have 6 what? I have 6 chickens. I have 6 cars. I have 6 pieces of pizza. I have 6 sixths. It now represents that second part is actually a physical quantity, So we can call that a sixth. And that's another sixth, and that's a sixth as well. But if I look at that shape, that's not a sixth anymore, that's a tenth, as opposed to that shape, which is a third. Right? So that gives us some sort of idea about how to construct that. So we won't go through all of these, okay, using each of those to shade in certain parts. So you can now see the shaded part is described by the numerator. And the denominator is telling you what the shape of that piece is. Okay? And we talk about equivalency and so on. So now in order to add fractions, we're finding the number of parts out of the same whole, and that's the idea here. And so there is another activity that I'll refer you to back here, referring to adding fractions. So this was created by a student here. We actually have or a group of students that come up, they actually show on these poster boards or just on a board, give them a dry erase marker or whatever. And they want to add 1/2 plus 1/3. So they've already learned how to represent it visually. And I always make sure that they draw their squares the same size, right? Because that means that this is one whole, and if I draw a tiny little square, that's not really the same size whole, right? So 1 out of 2 parts, 1 out of 3 parts, and I want to add them. And the problem with that is they're not the same size whole. They're not the same parts, the same size pieces. So the way that we visualize this is that we can kind of flip this fraction on its side. No reason we can't, right? Make them horizontal pieces instead of vertical pieces. And so if there's 2 pieces here, we could cut the thirds into 2 pieces horizontally. Or if this is 3 pieces, we could cut the 3 pieces into 2 pieces horizontally. So now we can see that they have 1, 2, 3, 4, 5, 6 equal parts. This is a good time to discuss with them that this is also a sixth. We talked to them about the shape of that sliver being a sixth, but now we see that this is the same size as that sliver, which now shows us that we haven't done anything different. It's still the same amount of shading. The only difference is that I've now cut those pieces into more, and now I can count the number of sixths that I have, which gives me a total of 5 of them. So you can then show that in a single whole as the fact that a 1/2 plus a third gives me a total of 5/6. So it's the visual that's important here, so that they realize it's not just, well, we all know we need a common denominator, add and subtract, because then what happens when you go to divide and multiply, they find a common denominator. Without really understanding why they need one, right? But it's about the fact that it's adding now. So it's the same thing like this, 3/4 plus 3/5. Larger fractions, not as easy as a 1/2 and a third, obviously. So what do we do here? What do we do here in order to add these fractions visually? Yeah, you kind of flip it. You make those 3/4 by drawing 5 lines horizontally. So you cut the fourths into 5 horizontal parts, and then you cut the fifths into 4 horizontal parts as well. So we now just say if there's 5 parts here, I could cut this into 5 horizontally, and it's the same fraction, which is why we discussed the equivalent fractions before. But this fraction is written differently. Even though it's the same quantity, it just looks different. So of course that, if I not only made the number of total pieces 5 times as much, but I've made the number of shaded pieces 5 times as much, which is why you can demonstrate why you're multiplying by 5 over 5. You're doing the same operation of both. And of course now they're the same size. Now you can combine them because they are the same size. Okay? Which gives us 27/20ths. That's kind of odd, right? Because what we notice about that fraction is a little different than other fractions we've been dealing with. How can you have 27 parts if you only had 20 to choose from in the first place? So that must mean that you've got more than a whole, which is why we have one whole with 7 extra parts, right? All right, so why don't we go ahead and try one of these on your own then? So, I'm saying that this may even be, it probably is even a new way for even many of you to think about this or represent this. So it does take some practice in a lot of the things that we do, even though we know how to add fractions. A lot of the activities that we do, it does take some work beforehand. Make sure that you're trying some of these before you do them, right? Okay. So I'll just take I'll say maybe 3 volunteers to come up and show us how you decided to construct this. Okay? Yeah, the 1 over 2 plus 1 over 6, we'll go ahead and head on to the dot cam right here.
Oh, you're right.
Yes, I do.
No, I
Or
didn't
if you want to bring it, if you bring that, we can
Afterwards
just put it on the dot cam and you can show it.
No.
Answer to 6. 10 mistakes.
I broke it.
Oh, yeah.
It made you.
All right. Go ahead and talk through what you did to construct that.
So first of all, I divide one half, and then this supposed to be just one half. And then this one 6 vertical. And then the idea is to make this in 6 parts horizontally. If you look to the denominator here, go here, and then divide this one into 2 halves horizontally. And then you shade again 1 half with the other here. So I have 1 half is 1, 2, 3, 4, 5, 6 out of 12. And then I have 1 6 is actually 1 2 out of 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 6 12 plus 2 12 is 8 12. So I have this one, and I get the result.
Very nice, thank you. Did anybody do it exactly the same way as that?
So the
Okay,
idea
good,
is what I
good.
noticed is look to the denominators and take to the other one.
Yeah, which is really the idea here that we were trying to show them. What could be the issue, though, that we run into if we do it that way?
Yes.
The fact that that you're missing the least common denominator part, right? Okay, so at that point, he said, Keith said, should we reduce this? Okay, now I'm going to be, I'm just going to mention one thing. I would try to encourage you to not use the word reduce, because reduce typically means make smaller, right? And so it appears oftentimes that when you are reducing 8/12 into 2/3, that you've made the fraction smaller, when you kind of really haven't. So I would encourage you to say simplify, and I know it takes some time because I was trying to modify that too, and I'll say, so we need to reduce, we need to simplify the fraction. But yeah, so we do definitely want to talk about simplifying that fraction, right? About the fact that 8 out of 12 could be simplified, and that's why you also had the slide earlier about equivalent fractions. That 3/6 is in fact equivalent to 1/2, and you want to make sure to simplify that fraction. Okay? Did anybody do that differently? Yeah? Could you come up and show us yours? Keep in mind what the main objective is of this activity. Making both squares have the same size. Right? Making both squares have the same size pieces.
Well, after I started by cutting this guy into 2 pieces, and this other guy into 6 pieces, I can mention to them that, do you agree that somehow this 1/2 here is the same as the 1/2? And then if that's the case, do you agree that this 1/2 had 3 pieces which I can cross here as well? That all of them are based on 6s instead of the 12? They can see that. And if they can see that, then I see that these are 3 over 6 and this 1 over 6. To make it 4 over 6.
Which then again, you could write down on the board along with 8/12 to show that sure enough, it does turn out to be the same amount. Okay? And so I think that after demonstrating the procedure that we did by flipping the fraction on its side, then they could see sure enough that it does work. But maybe demonstrating this, if in fact you notice as you're walking around that somebody had the forethought to do this process, again, call them up to discuss it. Yeah, thank you very much. Okay, so I think we're done with adding. Let's move on to multiplying, because I think this is pretty awesome. Great, so now go ahead and draw the picture for 12 13ths plus 7 eighths. Oh my goodness, that's right. So this is where they should be having some sort of understanding by doing these prior problems of what they were really doing. How did they add these? When you knew that you had to have 15 parts here after you counted them, where did that 15 come from? When you knew you had to have 8 total parts here after you added them, where did those 8 parts come from? Right? Which now means that they should be able to extrapolate that idea in order to do this without having to draw the pictures. But look at what this problem asks us to do. It doesn't say add, it says estimate. Because all we want to do is get them to think about how much is this. That's about 1, that's about 1, the answer is about 2. So what if they get an answer of 7 eighths? It's obviously not going to work, right? Or I don't know, whatever that was. But the idea is it closer to 0, 1/2, or 1? The funny part about this is neither. Closer to 2. But what about this one? 1/8, that's pretty small. That's pretty close to 0. That's pretty close to 1. That's something that's close to 1 plus the small fraction is going to be even closer to 1. Right? To give them some sort of understanding about how large are these fractions. Because I think that's a big deal with our students as well, is that they have a tough time even visualizing what a fraction means.
Kind of like a sanity check.
What's that?
A sanity check.
Yeah, there you go. And now finally, without using the squares, let's find these. Okay. All right, so how about visualizing how to cut 2/5 times 3/4? And I'll tell you, I was just so blown away by this, and I just love this aspect. But how can we visualize multiplication now? Okay, so if I say 2/5 times 3/4 by cutting a square, then what if I were to say 2/5 times 5? What does that mean? It means to start with the whole of 5, the second quantity, and take 2/5 of that. So if I want to take 2/5 times 3/4, what should I be starting by drawing? 3/4. So I should draw my 3/4. But now what I want to do is take 2/5 of that 3/4, which is why we're going to do something very similar to the way we did with adding. Cut them horizontally into fifths. So if I now cut them horizontally into fifths, now I want to find out what is 2/5 of the shaded yellow 3/4. But if they're cut horizontally into fifths now, I should be able to shade 2/5 horizontally. So I know that now, if this is 2/5 horizontally, while this was 3/4 vertically, what would we say 2/5 of the 3/4 is? Just the overlap, because of the fact that we're now saying the 2/5 out of the total of the yellow is purely the overlap, and now we can count them just like we did before. 1, 2, 3, 4, 5, 6 pieces out of a total of the 20 pieces, which is where we see eventually that we simply multiply the numerators and multiply the denominators. There's a reason, right? It's not just, here's the rule for doing it, make sure to do it. It's giving them an understanding of the fact that multiplying is taking a portion of a portion here. It's a portion of a portion, right? Which now means you could, of course, simplify that. So why don't we try 2/3 times 4/5? Let's try that one.
The diagram. In the future, what we say is like, hey, in the future, don't using this one anymore, just using like the way we multiply together. Okay.
All right, so go ahead and talk to us about what you did first.
Okay, so the first thing that I did was I partitioned it into thirds vertically, and then I did fifths horizontally. And I have done this before, but I usually don't shade in the 4/5 like completely, or I might shade them incompletely and really lightly, and then just kind of darken off the area where there is overlap. So I am missing those pieces.
Yeah, and that's another thing, actually Elizabeth does that same thing.
Yeah.
Because really, if you look at what she's doing, she drew the 2/3 and then really that piece that's not shaded doesn't even matter anymore. Because now you're just saying, take 4/5 of the 2/3. The 2/3 is all that's necessary anyway, so she just.
Just saying, like, where is it going to overlap?
Yeah. Thank you. Did anybody do that differently?
I wrote down the fractions on the left hand side, 4/5, bottom, 2/3. So you know, they will see that it's actually multiplying the fractions.
Okay, yeah, so you actually wrote the fractions to show that what the fractions are that are being multiplied. That's good.
There's colors, 3 different colors.
Good, so you do different colors. A lot of people, you'll notice, will do the colors. Some that only have pencils would do crossing in one direction, crossing in another direction, okay? Also, I would encourage you to recall, not that it matters because we know that by the commutative property, we're gonna get the same answer. But, keep in mind, you normally want to start by drawing the second fraction because of the multiplication being of, right? 2/5 of 3/4, which means we have to start with 3/4 and then take 2/5 of that. Now, really, it's the same quantity because you're just flipping the square, but since we've already been exposing them to constructing fractions vertically, we want to maybe start with that second fraction, okay? Now, what's cool about this, though, I won't do it just based on time, but what about 2/5 times 4/3? What would you do there? You should try these, by the way, because it is important so that you're not just stuck on the board like, wait a second, hold on. Like, you can't even do the problem, let alone
Do
Mm-hmm.
you
the
need
students,
two
right?
holes for 4/3?
Yes. So what would you do here? What would you draw?
One
One
hole.
hole.
Yeah, so we would basically draw 2 holes. And then what?
See what overlaps.
Well, you cut them into thirds, right? And then you'd shade 1, 2, 3, 4 thirds, right?
5 vertical.
Now cut into fifths vertically, or horizontally. 1, 2, 3, 4, and 5. This is where we can now shade 2 of those. And now this is kind of the tricky one. Because what do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8 out of 15, which is the amount in one hole, not the total amount that you cut into, right? So just keep that in mind because it's the total hole, which is why you get 815. So the picture looks different, and that's what's really important. Is that, and we even talked about it in pre-algebra, in 520 as well, about what does 2 plus 3 mean as opposed to 3 plus 2? They're not the same. They might give the same quantity, but those have different meanings, right? You start with 2 and 3, that's different than starting with 3 and adding 2. So the picture will look different when you do it in a different way, okay? So now I just want to show, obviously at this point, this is where we should realize that they're really just multiplying the numerators and the denominators, right? Once they get to that point, the pictures aren't necessary anymore. So now with division, this seems to be a tricky one at first, okay? But it's really important to realize that when you're talking about division, and I even tell this to my children, you know, it's like when you're dividing, what does 6 divided by 3 mean? And you start with the words how many. How many what? What does that 6 divided by 3 mean?
How many 3?
There you go. How many 3s are in 6? So how many groups of 3 are in 6? So how would we construct this? What do we start with now? You start with 6. You start with the thing that you're breaking apart. So you start by drawing 6 holes, right? So in this case right here, 1 hole looks like that. So now we're going to do 6 holes. Notice the difference with division though. We're drawing rectangles. There is a reason, okay? But it's easier to maybe think of a hole as rectangles in division. So if I separate that into groups of 3 by just shading 3 of each of those, we're now asking again, how many groups of 3 are in 6, and how many groups of 3 do we see? 2. 2 groups. There you go. So really I can bring those together to get two whole groups, which is why 6 divided by 3 is 2. Now this kind of seems obvious and intuitive when we're talking about integers, right? Which is why you could try some, obviously, of the integer values. What about this one? 1 divided by 1/5. So now what does that mean? How many 1/5 are in 1? So when you ask this about what does 2/3 divided by 4/5 mean, and then they pause and nobody says anything, you just refer back, what did 6 divided by 3 mean? How many 3s are in 6? So this means how many fifths are in 1? So what do we start with? We start with the 1 whole. So we're going to start by drawing one nice long rectangle, 1 whole. And now what I want to do is ask how many fifths are in 1. Well, I don't see any fifths in 1. So cut them into 5 equal parts. So I'm going to separate that, and now I can count them again and ask the question yet another time. How many fifths are in 1? 5. So you can count them and you can shade them each a different color, right? There's 1/5, there's 2/5, there's 3/5, there's 4/5, and there's 5/5. So 1 divided by 1/5 means how many fifths are there in 1, which is why the answer is 5. And we know that that's because we multiply by the reciprocal, but that's a rule, right? We don't want to just think about a rule. So then you could try some to where you're just dividing by unit fractions or dividing wholes by fractions. I want to focus on this one. Okay? So now what does that mean? How many 1/4 are in 1/2? How many fourths are in 1/2? So what do we start with? 1/2. But how do you draw a half? You have to first draw the whole. So you have to first draw a hole, cut it in half, and now all we're dealing with is the yellow. So now we're saying, in 1/2, how many fourths are there? Well, I don't see any fourths. So do I cut the whole into fourths, or do I cut the half into fourths? You can do it. So this is the tricky part, because notice that how many fourths are in 1/2? The fourth still refers to the whole. So that fourth still refers to the fourth of a whole. So that means that I've got to cut that whole into fourths, and now ask, how many 1/4 are there in 1/2? 2. And again, it starts to develop their idea of, well, why don't we just multiply by the reciprocal? They're going to keep asking those kinds of questions. Why don't we just, I already know how to do that. Why don't we just do this? It's like, because you don't get it. You don't understand why you're doing it, right? Which is why you can see from those student surveys that they appreciate the fact that they're learning why this works, so that it gives them some sort of better internalization of why you can do this.